Now, as indicated at the end of the last part of this lecture, we will use part 3 to introduce in more detail solution concentrations in units of molality and mole fraction, but we'll also see how these two relate to molarity and even to percent mass. Recall the definition of molarity. Molarity is simply the number of moles of solute divided by the number of liters of solution. We can compare this to the concentration unit molality, which is defined as the number of moles of solute divided by the number of kilograms of solvent. Note in just the name, molarity and molality, it's just a difference of one letter. The symbol for these two are different, but the most important thing is to realize that the denominators are totally different. So in molarity, the denominator contains the volume of the solution, the volume being in liters, and in molality, the denominator involves the mass of the solvent, in this case kilograms of solvent. Recall from a previous slide, we looked at an example of the preparation of an aqueous solution of glucose. In fact, we talked about how 95.882 grams of glucose was dissolved in about 200 milliliters of water. This was quantitatively transferred to a 500 milliliter volumetric flask and then diluted to the mark exactly on the flask. So we have a total of exactly 500 milliliters, at least known to the hundredths place. And then we capped that flask and mixed to make sure everything was mixed well. What we want to do here is calculate both the molarity and the molality of the glucose in this solution. Well, recall that determination of the molarity is straightforward. In fact, we've done this calculation. The 95.882 grams of glucose turns out to be 0.53222 moles, and the molarity turns out to be 1.0645 moles per liter. Now for the molality. Well, the molality, at least the first part, is easy. We've got 0.53222 moles of glucose, but we want to divide by the number of kilograms of solvent, in this case kilograms of water. We don't know what that is. So what we're going to do is actually, on the next slide, restate this situation, and we're going to provide a little more experimental information that'll help us find the number of kilograms of solvent, in this case kilograms of water, in this solution so we can finish this calculation of molality. That piece of information we're going to include is the density of the solution. So what I've done here is I've restated this situation and added some new information in these pink italics. So after the solution is prepared, a small but precisely known volume is removed and weighed in order to determine the density of the solution. And the density of the solution was determined to be 1.062 grams per milliliter. So we have our same situation. We want to calculate both the molarity and the molality. Well, recall we've got the molarity question settled. We're stuck on the molality part. What we need to do is obtain the mass of the water, the mass of the solvent used, and we can do this by using the density information. What we're going to do is determine the mass of the entire solution. So the mass of the entire solution would be the density, 1.062 grams per milliliter of solution, times the fact that we have 500 milliliters of solution. So we have 531 grams of solution. We can simply now subtract the mass of the solute from the mass of the solution to obtain the mass of the solvent water. So here we have the mass of the solution. We subtract the mass of the glucose, which gives us the mass of the solvent water. Note here I'm carrying an extra significant figure for a little bit. Then we can simply convert the mass of the solvent to kilograms and use it in our molarity equation. So to get molarity, molality, we need the number of moles of glucose, which we have, divided by the number of kilograms of solvent, which I've gotten from just converting grams of solvent to kilograms. Remembering that I really only have 4 significant figures here, we get a molality of 1.223 moles per kilogram. The kilogram here is kilograms of solvent or water, or 1.223 small m. So far, our aqueous glucose solution that we talk about has a density of 1.062 grams per milliliter, a molarity of 1.0645 molar, and a molality of 1.223 molal. The concentration unit molality may seem a bit strange, and it seems like it's very close to molarity, although it's a completely different number. So you might ask, what is this useful for? That is molality. Turns out it's the unit of choice for determining how certain what we call colligative properties of solutions, such as freezing point and boiling point, change with changes in solute concentration. This will be covered in future slides. Molality is also a great way to describe the concentration of a solution under circumstances where you think the temperature of the solution might change. Since mass is not temperature dependent, molality won't change when you change the temperature. However, molarity will, because the volume of the solution will change when you change the temperature. Let's now move on to calculating the mole fraction of glucose in this same solution. So I've restated the problem here, or the situation. The density information is now in green, and our job is to calculate the molarity, the molality, and the mole fraction of glucose in this solution. We've already done the first two, so we'll concentrate on calculating the mole fraction. Well, let's write out the definition of mole fraction applied to this particular situation. The mole fraction, which we often symbolize by this capital X, I think more properly it's a Greek letter chi. The mole fraction of glucose in this situation would be the number of moles of glucose divided by the total moles of everything in solution, which in this case is glucose plus water, and we'd symbolize it like this. Now we already calculated the number of moles of glucose in the mass of glucose given. It's 0.53222 moles of glucose. We can use the mass of water in the solution, which we determined previously to be 435.12 grams, to calculate the number of moles of water. So the number of moles of water would be the mass of the water divided by its molar mass, and we get 24.153 moles of water. Again, we're carrying an extra significant figure here, so this actually only has 4 significant figures. Now we're ready to calculate the mole fraction of glucose. So we have the number of moles of glucose divided by the number of moles of glucose plus the number of moles of water on the bottom here, and we get a mole fraction of 0.02156. Remember, in mole fraction, the highest number you could get is 1. So this is 0.02156. And the other thing we've done here is we've kind of quietly dropped the labels glucose and water here to make sure you realize that mole fraction does not have units. We're basically just counting things. By definition, the mole fractions of all components of a solution would sum exactly to 1. Therefore, we could calculate the mole fraction of water in the solution. The mole fraction of water would basically just be 1 minus the mole fraction of glucose, so we get a mole fraction of water of 0.97844. You might ask, what's the deal with the seemingly absurd number of significant figures? Well, it turns out that the measured quantities used in this long-running example with glucose were reported with high precision to several decimal places. It's not impossible to do this. In an undergraduate general chemistry lab, you probably would have less precision on the balance, so the number of significant figures you'd be dealing with would be less. Now, many examples you see in textbooks and problem sets will also not use quantities of such high precision, and so it won't be unusual to see fewer significant figures being carried and reported in other example problems. Let's restate our example situation once again, and this time we'll add the request to calculate the mass percent of glucose. Now remember, we covered mass percent earlier in part 1 of this lecture. So now we have the same situation with the same information, with a request that you calculate the molarity, the molality, the mole fraction, and the mass percent of glucose in the solution. Now I've worked my way up here to being able to calculate all 4 of these quantities from this information. And the reason I've done this is that it's not unusual for students to see situations, problem sets, where you'll be asked to calculate several different concentration units from the same piece of information. From previous slides, we already know that the solution is comprised of 95.882 grams of glucose and 435.12 grams of water. So the mass percent of the glucose would simply be the mass of the glucose divided by the total mass of solution times 100. We get 18.06%. So we can now summarize 4 valid ways of expressing the concentration of glucose when a 500 milliliter aqueous solution of this density contains 95.882 grams of glucose. We could say the mass percent is 18.06 of glucose. The molarity of the glucose is 1.0645 molar. Molality 1.223 molal, or the mole fraction is 0.02156. These would all be valid ways to express the concentration of glucose in this solution. Now additionally, since this solution consists of just one solute dissolved in the solvent, water, we can also easily determine some quantitative information about the solvent. So as shown on the previous example, the mole fraction of water is 0.97844. So if you're counting things in the solution, this mole fraction means that almost 98 out of every 100 molecules you come across in the solution are water molecules. Only about 2 out of every 100 would be glucose molecules. Now this is not too surprising after all, since water is the solvent and should be the thing the solvent is defined typically as the component of the solution there in the greater molar quantity. However, interestingly enough, from a mass or weighing perspective, the mass percent of water is 81.94%. That would be so because basically you're taking 100% and subtracting the mass percent of glucose. Well, what does this tell you? Well, if you're weighing, the solvent water takes up about 82 grams out of every 100 grams of solution, as compared to if you were counting, the solvent water takes up 98 out of every 100 molecules in solution. Now, this seemingly contradictory information just reflects the fact that each water molecule has a mass that's about 10 times less than each glucose molecule. Let's try one last example on the next slide. Let's suppose you have an aqueous solution of hydrochloric acid which contains 10% HCl by mass and has a density of 1.0474 grams per milliliter at 20 degrees C. The question here is what would be the molarity, the molality, and the mole fraction of HCl in this solution? Well, if you think about it for a second, it's difficult to tackle this question because neither a volume or a mass of solution is given. A common approach in this case is to simply assume you have a certain quantity of solution. So in this case, we will assume we have 100 milliliters of this solution. So let's see if we can calculate the molarity of HCl. Well, what we're going to try to do in a roundabout way is figure out how many moles of HCl we have in this assumed 100 milliliters of solution. So assuming this 100 milliliters, we can get the mass of the solution by taking our assumed volume and multiplying by the density to get 104.74 grams as the mass of the entire solution. Well, if the solution is 10% by mass, HCl, then 10% of this 104.74 grams is HCl. So we have 10.474, I'm carrying some extra significant figures here, 10.474 grams of HCl. Therefore, the number of moles of HCl in that 100 milliliters would simply be our mass of HCl divided by the molar mass of HCl, and we'd get 0.28727 moles of HCl. Because of this 10 grams here, we're really only allowed 3 significant figures, but we're carrying a couple extra here for a minute. And finally, since we have the number of moles of HCl, and we have the volume of the solution, which would be our assumed volume, we can get the molarity of HCl. This is the number of moles divided by our assumed volume in liters to get a molarity of 2.87 molar for HCl in this solution. Now let's see if we can calculate the molality of HCl. Well, we have the number of moles of HCl from our previous calculations. What we need is the number of kilograms of solvent, or the number of kilograms of water. Well, we ought to be able to do that because we know what the mass of the entire solution is. If we subtract the mass of the HCl, we're left with a little over 94 grams of solvent, which we convert to kilograms, do the division, and we get a molality of 3.05 molal. Let's look at how we might calculate the mole fraction of HCl in this solution. That was the last thing we were supposed to do. Well, the mole fraction of HCl would simply be the number of moles of HCl divided by the number of moles of everything in solution. That would be the number of moles of HCl and the number of moles of water. So we have the number of moles of HCl. We can get the number of moles of water by simply converting our mass of water into moles of water using the molar mass of water, and we put that right here. And so our mole fraction of HCl turns out to be 0.0520. So for this example, we have the mass percent of HCl as 10%, that you were given that in the question, the molarity at 2.87, the molality at 3.05, and the mole fraction of HCl at 0.0520. Question: could we have solved this problem by assuming 100 grams of solution rather than 100 milliliters of solution? Well, let's try it out. Let's see on the next slides. So here's our original question. And let's just assume now that we start with 100 grams of solution rather than 100 milliliters. How would we go about working with this problem and calculating the molarity? Well, assuming 100 grams of solution, the volume of the solution would be 100 grams times a reciprocal of the density. We'd use the reciprocal of the density in order that grams of solution cancels out and we have milliliters of solution. And if the solution is 10% by mass HCl, the mass of the HCl would be 100 gram solution times 10 grams of HCl per 100 grams of solution. In other words, the mass of the HCl is just 10% of the mass of the solution. And since we assume the solution had a mass of 100 grams, we have 10 grams of HCl. Therefore, the number of moles of HCl in the 100 grams of solution is, converting 10 grams of HCl to moles would be 0.2743 moles. And so finally the molarity can be determined. It would be the number of moles of HCl divided by the number of liters of solution, which would be the number of milliliters of solution converted to liters, and we get a concentration of 2.87 molar. How about the molality of HCl? Well, the molality would be the number of moles of HCl divided by the number of kilograms of water, and this is easy. It would be 100 grams of solution minus the 10 grams, which is HCl, leaving us 90 grams of water, or 0.0900 kilograms. And this gives us 3.05 molal. Let's calculate the mole fraction of HCl. The mole fraction would be the number of moles of HCl that we determined divided by the number of moles of HCl plus the number of moles of water. Well, the number of moles of water is simply the 90 grams of water converted to moles. And if we do that calculation, we get 0.0520. So if we start solving this problem by assuming 100 grams of solution, which we just did, the 10% HCl solution turns out to be 2.87 molar, 3.05 molal, and a mole fraction of HCl of 0.0520. If we start by assuming 100 milliliters of solution, which we did originally, we get exactly the same results. So despite some differences in the intermediate numbers appearing in the calculations, the final results are identical, whether we start by assuming 100 grams of solution or 100 milliliters of solution. A final note here, solution concentration questions come in a wide variety of forms that are both similar to and different from the kind of examples shown in this lecture. Your task is to figure out a way to use the information given in any particular question to determine the number of moles or the masses of solutes and solvents in order to calculate the requested concentration units. And for some problems, more than one pathway will lead to the correct result.